Hi everybody. So I want to start out this video by just quickly answering that ridiculous question that was in your quiz. Remember, I'm just looking for your the quality of your analysis, not the correctness of it. And that first question had to do with this interesting thing we see when we look at this molecule. Okay, so we have NH3, household ammonia, and then we have this molecule. This is called nitrogen triiodide. And what we see is that this molecule here, NH3, is extremely stable, and this molecule here is extremely explosive. The moment anything, as you saw in the video, even just a feather touches it, we can have an explosion. So the question really is why? Well, why has to get boils down to two things. One is the structure or the shape of the molecule. And you're going to learn in today's lesson that when I say shape, I mean molecular geometry. That's another word for it. Shape affects function. Super important. The shape of a molecule affects what it does. Probably the most important thing in all of science. The shape of a molecule affects whether it's a solid, whether it's a liquid, whether it's a gas, affects receptor drug binding, etc. So if you look at the shape of these molecules, they both have, I'm sorry, I'm going to use black here. They both have the exact same shape. So when I draw the Lewis structure for NH3, we end up with a molecule that is pushed down into this pyramid, if you will. And this is actually in 3D. So you can imagine this being this coming out of the board right here and this going back. This shape is called trigonal pyramidal. Okay, and when you look at Ni3, Ni3 also has the same shape. So what do you think is it that's causing both of these molecules to be trigonal pyramidal? As I finish this up, what do you think it is? Okay. What it is remember that these here are covalent bonds, meaning there are electrons in those bonds. And these lone pairs here, those are electrons also. And what do we know about electrons? Okay, we know that electrons are negatively charged. So if you get two electrons next to each other, they want to go away from each other. So these lone pair electrons and these lone pair electrons all want to get away from each other. But they're locked into these covalent bonds. So what's going to happen? What happens is the molecule conforms to a shape that minimizes the energy, right? So in layman's terms, these electrons want to get away from each other, but this molecule has to stay together. So the molecule forms a really comfortable shape that keeps it together, but gets the electrons as far away from each other as possible. If this lone pair wasn't there, this bond would scoot right up there. So now because of that shape, what happens is these H's are forced to be closer to each other than they really normally would be. And same thing with these I's. Well, what's the difference here? Okay, these H's are really, really, really tiny molecules. So if I drew this actually according to the shape, if this is the N, these are the little H's, okay? Now, if I drew this one, according to the shape, there's the N, and these are the I's. So if you notice here, these I's are closer to one another than those H's. And because these I's have these lone pair electrons near them, because they're very close to each other, if you get them just a little bit closer, these electrons are going to repel each other. Okay? So what happens in nitrogen triiodide, because the shape forces these three H's and these three I's to get close together, okay? If they are very large, there could be the chance that these electrons could interact right here. And if those electrons interact, the molecule itself will get just split right open. So that's what happens. These I's are so big that the covalent bond between the I and the N is really, really weak because these neighboring I molecules repel each other. And when they repel each other, the molecule could fall apart. And that's the explosion that you see. We don't see that with the H's. And so let's look a little bit more at this shape phenomena. So I just want you to watch me play with this simulation right here. So this simulation here just allows me to take a central atom here and allows me to put some bonds on it. So I'm going to put a bond on each side, and when you see that, it's straight. But what happens when I put a lone pair on the top? Oh, it bends the bond, right? So let's try that now with double bonds. Have this here, okay? Put that on one side. What's going to happen when I put a lone pair? Oop, it bends the bond because these electrons want to get away from each other. All right, let's try it differently. What if I put one here, and one here? Okay, so that's not trigonal pyramidal. This is called trigonal planar. What's going to happen when I put the lone pair? Oh, there it is, right? So there is that molecule that we just saw earlier. If these were really big, that would have been like the Ni3. Let's remove them all. And let's put 4. So if we put 4, a lot of times you think that there would be this cross, but what we see is we don't see a cross. We see what's called a tetrahedral, because these bonds actually are trying to get as far away from each other in 3D as possible. Let's look at some real molecules here. There we have H2O. Notice that those lone pairs pushing the bond down. CO2, there's no lone pairs on that central atom. SO2, there is a lone pair on the central atom. BF3, no lone pair, stretching it out. CH4, no lone pair. So we got a lot of things going on here. But the central premise of this all is that the bonds want to get as far away from each other as possible, and the lone pairs want to get as far away from the bonds as possible. So because there's not a set place in your notes to write this down, I'd like you to just find somewhere blank in your packet, and we're going to make a little table. Okay, so this table, we are going to have, I'm kind of slow there, molecular geometry. That's going to be one column. And in this other column over here, we're going to call this model. So we're going to make a model of it. Okay, and in the final column, which we want to be kind of big, this is going really slow right here, I apologize. We want this to be examples. Okay, so all right, so we're going to do this in red. So the first type of molecular geometry is a molecule that is linear. Okay, and the model for a linear molecule would be a central atom on this side and models here. Okay, another way of getting that would be something like that. And another way of getting that would be something like that. Okay. Now, this one here is not that common. We're not really going to be dealing with that one right here. But these two are really, really common. Notice there's a trend here. With a linear molecule, we have no lone pairs on the central atom, and we just have 2 atoms attached. So what's an example of that? Well, probably the most common example of that is carbon dioxide. Okay. Now notice, carbon dioxide does have lone pairs on this exterior O, but it does not have a lone pairs on the central atom. Okay. Another example of something like this is hydrocyanic acid. And notice there are lone pairs here, but none on the central atom. So that is an example of that model right here. And that's an example of that one right there. Okay. The next shape that we can have is a shape called bent. Okay. And there's 2 ways of getting bent. And again, bent is exactly what it sounds like. It's bent right here. One is with 2 lone pairs on the top, and then the other would be one like this, 1 lone pair at the top. Now there's 2 lone pairs here, obviously, to get 2, 4, 6, 8, and 1 lone pair here because there's a double bond, 2, 4, 6, 8. So what's an example of the first one? Well, that's water. That's our standard example. And water being bent is really important. Okay. And sulfur dioxide is a common one here. So There is your example of that one, and there's your example of that one. Okay. After bent, okay, I don't have a lot of room here. I'm kind of running out of space. So what I'm going to do here, so let's see, what can I do? Oh, you have linear, you have bent. I'm going to do one more here. We have what's called trigonal planar. Okay. And in trigonal planar, we have a model that can look like this. Or we can have a model that looks like this. Okay, so one thing you notice about this is that there are three things attached now, but there are no lone pairs on that central atom, which makes it planar or fall into the plane of the board. And examples of the first one would be like BH3. Remember, B is an exception. Okay, or an example of the other one is formaldehyde. Okay. I want you to notice here again, three things attached, no lone pairs on the central atom. Okay. I'm going to move up here to the top. I want you guys to just keep moving down in your notes, but I'm going to use this space up here. So I'm going to erase these little friends, and I'm going to move up. We have two more shapes to look at. As I erase this, you're probably remembering this one actually that I'm erasing, ironically. That's their other shape. That's called trigonal pyramidal. And then we have the final one, which is called tetrahedral. Okay. So just kind of bear with me here. And as I'm erasing this, just want to remind you, it's really, all of this is so much about where that lone pair electron is. Is it on the central atom? Is it on the exterior atoms? Turns out to be really freaking important. Okay, so now remember, you're going to be down below. So the next one is called trigonal pyramidal. And the model for that is going to have this lone pair up here. And there's only really one format for that. Three things attached. Unlike that trigonal planar where this was up there, these lone pair electrons press it down. And a standard example for that is NH3 or Ni3. Let's go ahead and just do this one. Okay. And the final one is when you have four bonds. Okay. And that's called tetrahedral. Now with tetrahedral, it's not going to form an X. It's going to form kind of, imagine a pyramid down at the bottom. And instead of this lone pair, there's one right up here. And that's methane is a standard example of that. Okay. Now, in addition to the shapes, and let's remind ourselves, we have linear, that's a shape, that's with two things on each side, but no lone pair on the central atom, CO2 and HCN as an example. Bent, that's with either two lone pairs on the top or one lone pair and two things on each side. H2O and sulfur dioxide is an example. Trigonal planar, three things, no lone pairs. And here's an example of each of these. Pyramidals, when you have three things but with that lone pair on top. We saw that with the Ni3 and the NH3. And then tetrahedral here. There are set bond angles. Remember I said the molecule is trying to find the most stable way of being. So there are set bond angles, and that's what really gives it this geometry. So a linear molecule, the bond angle here is always, and you could probably easily figure that out, it's always 180. And we know in bent, okay, this bond angle here, it's always 104.5. Less than 180, obviously, because those lone pairs push. Trigonal planar, you could probably figure that out pretty easily. That's 120. No lone pairs, so super symmetrical. And it's going to be less than 120 with trigonal pyramidal because of those lone pairs. And it turns out that that's 105 degrees. And with tetrahedral, remember, it's not going to be 90. Okay, we don't do that. It breaks out into this three-dimensional tetrahedron, kind of like a tripod with a top. And that bond angle there is 109.5. So let's go through now every single practice problem we did, and let's indicate the molecular geometry for it. And what I'm going to do is I'm going to draw the Lewis structure here really quick, and you guys are then going to indicate the molecular geometry. So what I would do is I would pause me right before I draw the molecular geometry, let me do it, and then unpause me to see if you got it correct. So I'm going to go ahead and do it. CS2, and redraw the structure if you didn't draw it with the correct shape. Okay, so that's two things, no lone pairs, so that's going to be linear. pH3. Three things, and by the way, throughout all of this, I'm not going to do the bond angles, but you need to have those written down as you did over here. So that's going to be trigonal. I'm just going to write T pyramidal because of that lone pair pushing. 180 degrees, 105 degrees. OBR2. So some of these, if you don't have them drawn according to the correct shape that I did, I want you to please redraw them. Okay. Now these two don't balance each other out. They're kind of in 3 dimensions here. And that's going to be bent with 104.5 degree bond angle. Bent because you have two lone pairs and you have only two things attached. SO2. I imagine these ones you probably have to redraw. You probably drew them as linear initially. Okay, again, this is also going to be bent, 104.5 degrees. You have two things attached and two lone pairs. CF4. Okay, so as I do this, you probably should pause me and make sure that you got it right. Okay, now in this case, you have four things, no lone pairs, so that is going to be your tetrahedral. I'm just going to write tet. NO3. Boom. For the sake of time, I'm not going to be drawing the lone pairs on the external atoms, but I need you to. Okay, so there's three things attached, no lone pairs. So that's going to be T planar. Here we have C double bonded O, H, H. So again, that's another T planar. 120 degrees. You have three things attached, no lone pairs on the central atom. H, C, and okay. No lone pairs on the central atom. Two things attached, so that's going to be linear. CO3, 2 minus. So that's going to be -2. And again, no lone pairs on the central atom. So that's going to be, sorry about the speed of my pen here right now. That's going to be T planar. Okay. Ooh, N2 is an interesting one. We never went over that. But obviously, if you just have two things, the only thing that could be is linear. This is an interesting one. You actually have two shapes in this one. Come on. Come on, pen. You have H, 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 O, H. Okay, so I'm going to do it with a different color here because that carbon right there has 1, 2, 3, 4. So that is a tetrahedral carbon with 109.5. And then that O has 1, 2. So that's bent. And you're going to see that often. Okay, this is often something with large molecules. There's multiple molecular geometries in one molecule, and that again is something that affects its function. It's a really exciting thing. NH4. You guys don't care if I stay in black right here, do you? Oops. My pen is being really, really, really silly. So you know what? I'm just gonna freaking erase this. Whatevs. What? So yeah, got our brackets here. Got our brackets here. And H, 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 H plus. And that's going to be our old tetrahedral. Okay. So again, what I'm going to have you do is finish off all of these, and you're going to be turning that in for your check out, taking a picture of it. Take care.